school, such that the particular school prefers to enroll that student and the student prefers to go to that school. Now, a second concern in New York City was actually student welfare, and actually there was a huge congestion problem associated with the old system. More than, here it says 45, but in New York Times it is reported that more than 36% of students could not be assigned any school in their choice list. Now, this actually led to the decision of a student optimal stable matching mechanism, a variant of this in New York City. Now, what is the problem then? How can we formulate the problem? Well, the problem is our objective is probably Pareto efficiency with respect to student preferences. But we also have some constraints, incentive constraints. Some schools are active players. So stability for school incentives is a constraint on the problem, on the optimization problem. And student strategy proofness for students is also another constraint in our optimization problem. Yes?
What's the incentive for schools to conceal capacity? Are there like performance bonuses that they can get or anything?
My hunch is because of the congestion problem, there would be more than 36,000 students who remain unassigned. Schools would have the incentive to go and handpick from this.
So they want smarter students?
Yes, the students that they prefer. If you solve this congestion problem, schools would not be able to pick from such a big pool of students. And that would give them incentives to not conceal their capacity. And actually, if you look at the numbers over the years, number of students getting their first choices improve over the years. And that's partly probably due to the fact that schools are no longer concealing capacity. They are actually reporting full capacity.
Isn't the capacity known to the central authorities? How do they get away with this?
That is true, but not necessarily. So in most cases, yes. But in certain cases, no. And actually, one of the improvements in the system was if a school reports few seats, the Department of Education actually assigns more students to the school and ranks students in an order of some specified preference. So they try to give incentives to schools to rank more students in their preference list, as well as to submit higher capacities. But the charters, some schools also are more autonomous. For example, charter schools, they are not under the control of the district. You would need to give incentives to them to reveal their capacity. So now let's again work out a simple example. 3 students, 3 schools, each one with seat, and let's suppose that schools are indifferent among all students. So one thing we could do is we could assign a random number to each student and use that random number to break ties at every school. In this case, we don't have any priorities in this simple case. So every school would have the same ranking. And when we apply deferred acceptance, that would actually coincide with a random serial dictatorship. In this example, for example, if student 1 gets the best random number, he will pick his first choice. Student 2 is going to pick her first choice among the remaining schools. And student 3 is going to pick his best choice among the remaining schools. If student 3 gets the best random number, he will pick school 1, which is his first choice, and so on. Now that advantage of this is, in this particular example, each matching is Pareto efficient with respect to student preferences. Actually, in this case, there are no school preferences. And but one of the issues was about tie breaking. Are we going to use a single lottery number, or are we going to use a multiple lottery number? Actually, if you look at it here, student 3 gets the worst random number in that tie breaking, and actually he cannot get into his first choice, he cannot get into his second choice, he ends up with his third choice, because once he gets the worst number, he falls through the cracks and ends up with the worst choice. So one way of avoiding this maybe is to use school-specific lotteries. If every school used its own lottery, drew its own lottery, student 3 might have had a bad luck at school 1, but a better chance at school 2, right? And that actually came up during our discussions with the Department of Ed, New York State Department of Ed. And they insisted, and apparently some parents also insisted that the most equitable approach is actually to use school-specific lotteries. And why is this not a good idea, using school-specific lotteries? It is because, remember, this is an optimization problem. When we break ties at schools independently, we are actually creating school preferences and artificial stability constraints on our optimization problem. Those artificial constraints are going to start binding, and it's going to hurt school, our objective of student welfare. Here is an example. Student 1 gets the best random number at school 1. Student 2 gets the best random number at school 2. 3 gets the best random number at school 3. Run deferred acceptance here. Student 1 and 2 are going to get into their second choices. They would have been better off if they swapped their schools. But that matching cannot be produced by this random tiebreaker, because according to this tiebreaker, student 3, who prefers S1 more than S3, that's what he gets, also has a better random number at school 1 than student 2. So this creates a blocking pair, but an artificial blocking pair. There's actually no school preferences here, and that blocking pair is due to the random numbers, due to the tiebreakers generated randomly. Now, so that is actually that. One question then is, what can we achieve by single tiebreakers? A single tiebreaker is a special case of a multiple tiebreaker. One question is, are we missing then? If we focus on single tiebreakers, are we going to miss anything good? Well, it turns out not really. By finiteness, there's a finite set of student optimal stable matchings. And because of indifferences, this is no longer a single matching. When schools have strict preferences over students, and students have strict preferences over schools, there is a unique student optimal stable matching. That is no longer true when schools have indifferences. But each of these matchings, student optimal matchings, can be obtained by a deferred acceptance mechanism that uses a single tiebreaker. That is, there exists a single tiebreaker that generates that student optimal, any student optimal stable matching here. Pick one student optimal matching, you are going to find a single tiebreaker here. Well, of course, you are going to find a multiple tiebreaker too. It's the most general case. But that set is actually the set of matchings that can be, the set of stable matchings that can be generated by a single tiebreaker is actually a subset of the stable matchings that can be generated by multiple tiebreakers. What does this mean? This means anything that we can generate by a multiple tiebreaker, but not a single tiebreaker, is definitely going to be inefficient. So yes, we are going to be missing something when we use multiple tiebreakers, but we are not going to be missing the efficient ones. We are going to be missing the inefficient ones, which is probably good news for a single tiebreaker. Now, how does this translate into numbers? So what we do here is we take the 2003, 2004 admissions data, the school choice data in New York City, and we run deferred acceptance single tiebreaking, deferred acceptance with single tiebreaking, and deferred acceptance with multiple tiebreaking, and we look at the number of students who are assigned their first choice, number of students who are assigned their second choice, number of students who are assigned their third choice, and so on. We actually run a bunch of we run those each mechanism with a bunch of lotteries. I think we ran about 1,000 lotteries for each experiment, and we take the average of those numbers across all lotteries. Here, in comparison to deferred acceptance with multiple tiebreakers, the one that uses school-specific lotteries, there are about 2,000 more students who get into their first choice. Actually, looking at the and there are more students that are assigned their first or second choice on the single tiebreaking. There are more students who are assigned one of their first, second, and third choices on the single tiebreaking. There's a sense of a stochastic dominance relationship here, but it is actually not true. If you look at the numbers here, the number of unassigned students on the single tiebreaking is slightly larger than the number of students under multiple tiebreaking. There's actually that this provides slight evidence for that intuition that if I get a bad random number, if I get a bad luck, I'm going to fall through the cracks, and I'm not going to be assigned any of my choices. So theoretically, we don't know how those two mechanisms compare. Numerically, deferred acceptance with single tiebreaking in this example seems to dominate deferred acceptance with multiple tiebreaking up to the sixth choice. After that, multiple tiebreaking starts catching up. Yes.
Just to clarify, you're running these on people's reported lists?
That is people's reported lists,
and
correct.
So it's the reported first choice and so on.
Correct, yes. And I'm going to talk about this. Actually, there is an incentive issue here. In New York, there are students can choose from more than 700 programs, but they are allowed to rank up to 12 schools. So which 12 schools are you going to pick? There's some strategizing that might be going on there. But in this simulation exercises, we assume that those, we don't even need to assume. We just do this with respect to reported preferences. Yes.
You're saying that the deferred acceptance with multiple tiebreaking doesn't perform as well for the late choices. Would this change if you didn't have that 12th choice constraint?
I think that's a good question. I don't know. I think it would still be the case. I think deferred acceptance with multiple tiebreakers would assign a higher number of students to their higher choices for the lower part. So what does the simulation suggest? This is actually the kind of simulation we gave to simulation results that we gave to the New York City Department of Ed, and they were convinced by those simulation results, and that is how they chose single tiebreaking over multiple tiebreaking. Now, even a single tiebreaker might not be sufficient. Here's a simple example, actually the same example, but now suppose that those two schools rank students in a strict preference order. Only school 1 is indifferent. Run a lottery, and if it turns out to be this one, we obtain the same example. In that example, student 1 and 2 get into their second choices. And the reason why student 2 cannot get into her first choice is because, according to this random ordering, student 3 would block student 2 at school 1. That, again, is an artificial stability constraint that is created by a single tiebreaker. Now, we know that that is dominated by the matching in which 1 and 2 are assigned their first choices, and that is stable. There's no blocking pair here. So, how can you find? How can you find a student optimal stable matching then? Look, a single tiebreaker does not always achieve a student optimal stable matching. There's indeed a clever algorithm, stable improvement cycles algorithm, that works on top of deferred acceptance. That is due to Erdel and Ergin. By using that algorithm, we can characterize the set of student optimal stable matchings. Actually, that algorithm is can be generalized in a way that Gale-Shapley itself can be formulated as a stable improvement cycles mechanism. Starting from the empty matching, in which no student is assigned any school, we can find out all stable improvement cycles and achieve fully student optimal stable matching. So that mechanism is not strategy proof, but actually there is no strategy proof and student optimal stable mechanism. Well, what does this say? This says that Gale-Shapley cannot be student optimal, right? Because it is strategy proof. If there is no strategy proof student optimal stable mechanism, and if Gale-Shapley is student optimal, then it must be the case. If the Gale-Shapley is strategy proof, then it must be the case that it is not student optimal, and we have already shown it. But the question is, what is the trade-off between efficiency and incentives here? I know Gale-Shapley with single tie breaking is not efficient. So there is going to be instances where I can correct inefficiencies. But can I do this without harming student incentives? Now, remember this theorem. This theorem says that there is no strategy proof and student optimal stable mechanisms. What I am after is relaxing this part. I know I cannot achieve full student optimality, but can I at least improve on Gale-Shapley? That's the question I'm after. And actually, the answer is no. So, given any tie-breaking rule, there's going to be instances where the deferred acceptance with that tie-breaking rule is going to be inefficient. And if you want to correct those inefficiencies ex ante, then you are going to lose the dominant strategy incentive compatibility. And in other words, deferred acceptance, if we want to choose deferred acceptance with single tie-breaking, that actually lies on the Pareto frontier of dominant strategy incentive compatible mechanisms. That gives us a tight bound for what we can do. And here is an illustrative example of the proof, towards a proof. Here are, again, these two schools rank students in that order, and ties are broken at school 1 this way. And these are the students' preferences. Deferred acceptance would match student 1 and 2 to their second choices, and student 3 to her last choice. Let's suppose that there's actually a mechanism, a strategy proof and stable mechanism that actually improves upon deferred acceptance at that instance. How can this happen? This can happen only if student 1 and 2 get their first choices. Let's suppose such a phi exists, and that phi is a strategy proof. Now consider an alternative preference relation for student 1. student 1 only ranks school 2, and he states that other schools are not acceptable for him. What would deferred acceptance do? Well, deferred acceptance, run the student proposing deferred acceptance, it would leave student 1 unassigned, and student 2 would get, student 3 would get his, her first choice, and student 2 would get his second choice. What would phi do under this case? Remember, phi dominates deferred acceptance, right? So it has to assign something to 3 at least as good as S1, but S1 is her first choice. So phi is going to assign 3 the school S1. Given that S1 is gone, phi also has to assign something at least as good as S2, which is actually S2. There's nothing left. So phi is going to assign S2, and therefore phi is going to assign leave 1 unassigned. Now compare the assignments of student 1 here and here. Here, student 1 remains unassigned, and student 1 gets school S2 here. If this were student 1's true preferences, by stating his true preferences to the mechanism phi, he would remain unassigned. But if he actually adds school 1 to his preference list, he will actually get his first choice. So that illustrates intuitive example actually can be generalized to a proof, and we obtain those results. So what is this good for? As I told you, this theory, in the first part of this talk, I'm going to try to use theory to guide our empirical strategy. And the first example of this was the comparison of single tie breaking versus multiple tie breaking. This result, this negative result, actually tells me that deferred acceptance with single tie breaking is on the Pareto frontier of dominant strategy incentive compatible mechanisms. So if I want to keep stable matchings, and that's in a sense required in order to provide schools with the right incentives, what can I do? The best I can do is to go from deferred acceptance single tie breaking to a fully student optimal stable matching. That would tell me how much I lose by imposing incentives on students. Right? Because I know that I cannot improve on that mechanism even slightly without harming incentives. And if I go from this mechanism to fully student optimal stable matching, I would still give some appropriate incentives to schools, but I would break student incentives. Actually, then that comparison would give me a sense of the cost of imposing incentives on students. And how do I go from here to here? What I do here is I take a single tiebreaker, find the deferred acceptance matching. If it turns out to be inefficient, I find a student optimal stable matching via the stable improvement cycles. And I do this 1,000 times, and each time I compute the number of students getting into their first choice, and so on. And when I do that, here is the results that we obtain. There are about 600, on average 633 students who improve by 1 choice in their choice list when we switch from deferred acceptance to fully student optimal match. And there are about 340 students who improve by 2 steps in their choice list when we do this switch. And actually look at that. There are even 2 kids here who move from their last choice to their first choice when I switch from deferred acceptance to fully student optimal. So that actually tells us on average I can improve the assignment of about 1,500 students by switching from deferred acceptance with single tie breaking to a full student optimal stable matching. That gives us a sense of the cost of imposing student incentives here. Now, yes?
I suppose that also some of the students' assignment got worse?
No, actually that is an improvement cycle. So what does this mean? This means I am going to improve some students' assignments without violating stability. And how do I do that? Start with a stable matching. I like your matching and you like my matching. If we exchange our schools, we would be both better off. But can we exchange it without violating stability? We could if you are the highest priority student among those who prefer my school and who are not assigned. And if I am the highest priority student among those who are not assigned your school and who prefer your school. If we could identify those two students, and the stable improvement cycles algorithm allows us to identify such pairs or cycles, we can actually swap students without violating.
Is it like running cascading cycle with those assigned schools?
It is like that. We are going to find cycles, but on those cycles, we are going to impose the stability constraint.
Right.
So we cannot, of course, I may like your school more than mine, and you may like mine more than yours, but it doesn't mean that we can exchange it without violating stability. So I mentioned that stability arises as an incentive constraint in that problem. Why is that? Because when schools have preferences, the problem becomes a two-side matching problem. And there are no stable matching mechanisms that are incentive compatible for schools when schools have more than one seat. Yet you could think of stability as a way to limit the scope of manipulation for schools. Then what is the cost? What is the cost of imposing that incentive constraint on our optimization problem? One way to measure this is start with a student optimal stable matching. That's the best you could do for students by imposing stability as an incentive constraint for schools. Then from there, go all the way to a Pareto efficient matching. How can we do that? We can do that by ignoring stability and by allowing students to further improve their matching via exchanges. Yeah, that's where the top tiering cycles kicks in. Yeah, and when we do that, students who improve their assignment by one step in their choice list, that number is equal to 1900. And about 1000 students improve their assignment by 2 steps in their choice list after they exchange their schools. And in total, there's about 4,200 students who improve when we switch from a student optimal to fully efficient matching. But this does not come for free, actually. There's going to be a lot of blocking pairs. For example, there's going to be 22,000 students who are going to block matching at a single school. And there's going to be about 7,000 students who are going to block the final efficient matching at 2 schools, and so on. Now, in total, actually, by switching from student optimal to a Pareto efficient one, we are going to create about 35,000 blocking pairs. Now, that is a way to assess. That's how we use theory and some new theory to guide our empirical study of the markets here. But what else can the data say about markets? There's actually an immense amount of data that's coming out of those school